Hello. Okay, share. Right. Okay, click on here. Okay, so I think there's a couple people actually on, and not sure how we're going to do this because it's the first time I'm trying this, but let's start by you guys communicating by WhatsApp. And if you could let me know, or comments on here, I am really like 1,000 years old. Comments on here that it's working and that you can hear me, and then we'll figure out what to do next and whether this is a good idea. We could just switch to WhatsApp too, if you think this is a better idea. Kind of up to you guys. Okay. I posted the key for the quiz. I hope you had a chance to look at it. Don't touch your face. It's bad. Corona. Okay. Anyway, so I could hold up pieces of paper. Let's see how that works. Oh, there we go. It actually kind of does work pretty well. I've got it reversed on mine, but I hope it shows up the correct direction around for you. I believe it does, but I'm not sure. So it does look like that works okay. We do have 4 people on here now, apparently. What do you guys want me to do? We could look on WhatsApp whether anybody said anything there. No, nobody said anything here. I could just go about going through the questions. If you have any specific ones you have questions about, I could explain more in detail, or we can do something else. Hi, Octave. So yeah, while you're just thinking about what we should do, we could step our way through the quiz corrections. I mean, this quiz solutions. The first problem, just a reminder, well, hang on. This is the first problem in my version of the set. I don't know if you guys realized that questions were scrambled. We were asking for the magnetic field to the left of wire X by a distance of A. And the 2 wires are 2A apart. And they're asking for the total magnetic field at that point. So what's the trick here? Well, the trick is that magnetic field is inversely proportional if it's generated by a straight current. So it's 3 times as far away, it's 1/3. So the right wire produces 1/3 the magnetic field of the left wire. So the total magnetic field will be 4/3, or 1 plus 1/3, or 4/3 of the magnetic field created just by the big wire, the closer wire. They have the same current actually. So, okay. Sam, okay. I don't see any messages. Let me check here. I am on mobile data. I should be able to see it. Sam, I don't see your message. Do you mean from yesterday? Oh, okay. Well, I sent the solutions, and my solution works out, Sam. So could you look over that and see if it makes sense? Because I'm not sure I want to right now look through your entire solution right now. I hope that's okay from yesterday. I hoped that my solutions that I sent you today would answer your question. Okay. All right. Well, while we're just here and nobody's saying anything, I can just flip through these. Is this helpful? Somebody say yes or no. We can do something different. Okay. So here's what I have as question 2. This was about, I know, like there were 2 parts to this and they were scattered throughout depending on where you were. It was regarding an electron and a proton entering a magnetic field, and how would they behave differently? That's this question here. Now, a proton has 2 specific ways it's different from an electron. It has a positive charge rather than a negative charge, so the direction of force will be opposite. That makes sense. And the other important difference is that it's about 2,000 times as massive, which means that when it experiences a force, which is just QVB, then it would have a substantially lower acceleration, and therefore it would be deflected less. Okay, so the centripetal acceleration will be substantially lower because the mass is so much bigger, and therefore the curvature radius is going to be much bigger for the proton. Okay, I'll just keep going till you guys say something different. All right, here we have the next one. This is a wire loop. We only see 3 sides of it, of course, but it has to be closed somewhere else. And it's in a magnetic field, and it's experiencing some force here. And they're asking specifically as to what would happen if we turn this a little bit. Now, if we turn this a little bit, those 2 segments, whoa, here are my fingers. There, this segment and this segment doesn't really change anything because they're still in the same direction as the magnetic field. So they will not experience any force either way. Now, this guy here, when we turn this thing like this way or like this way, it's still at right angles with the magnetic field. And that means that the magnitude of the force will still be ILB, same one, no change there, but the direction will change because the direction of the force on the wire depends on the right-hand rule. So point your fingers in the direction of the current, curl your fingers in the direction of the magnetic field, and then you would see your thumb pointing in the direction of the force. And of course, if we do that, so right now we're pointing straight down in the direction of the current, and you can kind of already see, well, I got to turn it this way to get the force worked out. But if I now change the direction of the current, my thumb, by definition, would also turn. So a 10-degree turn for the direction of the current will also cause a 10-degree turn in the direction of the force on that loop. All right, keeping going here. And sorry about the small print. I hope it showed better up on the test itself. We're asking here specifically about the magnetic field and the electric field between two capacitor plates that could cause the electron passing through here not to experience any net force, because that's what we're saying here. If it's passing straight through undeflected, the net force has to be zero. And that means that electric and magnetic force have to be such as to cancel each other out. They need to be in opposite directions. Now, in order for that to happen, they have to be crossed. It doesn't work if they're in the same direction. That's important. So at least all of our requirements meet that. Do they? Yeah, at least that part. Yep, they all do. But then I went through and actually figured out using the right-hand rule what direction the direction of the magnetic force would be, and what direction the electric force would be. And in that regard, there's two important things to remember. That we need to have, for an electron, the fingers pointing opposite the direction of motion for the magnetic force. And for the electric force, we need to make sure that we remember that the electric force points the opposite direction of the electric field. The electric field points in the direction a positive charge would experience a force. So the electric force on a negative charge is opposite the direction of the electric field. And I go through the steps here. The 5 of them actually went all through, even though the first one already I hit the jackpot with the correct answer, that worked, but the other ones don't work. So if you look through in the first one, we see they are opposite each other. Second and third option, they are pointing opposite directions, and same directions, so they can't add up to 0, unless they're actually both 0. That's silly. Okay, then of course in the fourth and fifth option, they are actually at right angles, and there's no way they can cancel out there. So there you go. Is that correct? Did I say that right? Oh, no, sorry. In the fourth and the fifth one, what we have actually is because the electron is moving along the direction of the magnetic field, there will be no magnetic force, and therefore the electric field will create a force that's unbalanced for sure. All right, so let's keep going here. We're asking here for a little bit of an awkward spot in terms of finding the magnetic field at that location that's indicated. Now, what I did here was I used 3 different colors to help you realize the direction of the field at that point created by the 3 charges. The C charge I called red, the A charge I called blue, and the B charge I called green. Yep, that's correct. Okay, and then I kind of drew, not just kind of, I drew in approximate values. Now, 2 things that matter here, the direction and the magnitude. They're vectors. Yay, Mr. Blessman. Wow, awesome. Okay, so the key thing here is you use the right-hand rule. You point your thumb in the direction of the current, and then curl your fingers in terms of getting the direction of the circular magnetic field line about that central point, which is the current, which is at the center of the circle. Now, the other aspect here is that we're looking at electric field, so you shouldn't be drawing 3 circles because that would be super confusing. But the magnitude of that first, the direction is tangential to that circle, or it's perpendicular to the radius from the center to that point. So you can see the red line, for example, points straight up because that is perpendicular to the radius from wire C to the point P. And the magnitude of that force is the biggest because C is the closest. And the same things apply to the magnetic field created by A, again, perpendicular to the radius from A to the point P. And the magnitude is second largest because A is the closest, second closest. And B is pretty far away. But again, the direction of the magnetic field should be perpendicular to the radius. Did I screw that up? Hang on a sec. No, that's right. No, that's good. I got confused because it was upside down. I think we're all set. All right. Okay, yeah, it's all good. All right, and then if you add all three of those together, the one that's closest to that, so you can kind of see it's pointing to the top left because the green one really doesn't matter much. But that's the correct answer then, so the answer would be E. All right, so keeping moving here. Okay, so righty, here we go. We have here two currents, and we're asking for the magnetic field created at a point above there. Now, actually doing this correctly is a little schnickelig, and honestly, I thought this was a little challenging if you didn't have the answers provided, because I kind of got set on them like, well, theta is the angle at the top of that triangle, good. And then, well, we don't need theta. We need the angle in that triangle. And I think that angle is also theta. But then I got caught up in like, oh, there's supplementary, all that stuff, 90, whatever, supplementary, complementary lit angles and all that. I was like, I'm not 100% sure. But the nice thing is, because they provide us the answers down here, well, we know that the magnetic field created at point O by either of the wires is going to be mu naught I divided by 2 pi d. Okay, that's easy. We can write that down. And we also know that when they add, they have to add up to less than twice that because they're not in the same direction. So I kind of wrote that out over here saying, okay, well, we need the magnetic field total to be less than that value. Well, that's the answer here. So that answer is wrong. And once that answer is wrong, this is the only answer that can be right. So I kind of MacGyvered it backwards because I think in a multiple choice setting, this is a little tricky. So sorry about that, but it's workable, I think. And I hope that makes sense. Yeah, the bottom two answers can't be it because they're pointing in the wrong direction, and the top one can't be it because it's 0. Oh, wait. Which is this one? Sam, you wanted to look at, wait, crap. This one? No. Yes? No. Wait. You're still asking about this one, right? Okay, hang on. Shouldn't it just be vertical portions? Hang on. A. Oh, the angle one. Got it. Hang on. Hit this one. Yeah? Okay. It is just the vertical, this one, right? Okay. So this one, it is just the vertical portions. That's correct. Okay. It is the vertical portions is correct. And you kind of see that in the diagram, the way I set it up. I've got the red one and I have the black one. And I kind of indicate with the colors which wire is creating which magnetic field. They create the same amount of vertical component magnetic field, and that's why the resultant vector points straight down, and the vector you have there is correct. Now, yes, it's the vertical components, and you should use the cosine of the angle from the vector to the vertical, and then multiply that whole thing by the magnetic field, and then multiply everything by 2. The problem I'm running into is I'm pretty sure that's theta and somehow it's related to A and D and all that stuff, but maybe I'm being dumb. I don't think the geometry and trigonometry is super easy, so I just MacGyvered it backwards. Maybe that's unsatisfying, but I could think about it a little bit more and then post my solution. And Sam, I'll look at your solution and contact you in person, okay? Yeah, I'll look at it, Sam, again, and then I'll get back to you. Okay. Good. All right. Cool. Now, this might have scared the children a little bit. This was a torque question. But the nice thing is here, I mean, first of all, breathe. It's going to be okay. Second of all, they give you the equation for the torque. And third of all, well, we know there's a force on a wire inside a magnetic field. And if it's part of a loop that's turning, well, there's a lever arm, and R cross F is the torque. So this shouldn't be revolutionary as such. Now, if we look at this, they give us data and they come up with us with basically what they predict as the measured, calculated value, comparing it to the measured value, and it doesn't align right. And if you look at this, these are all basically about the idea whether one's bigger than the other or the other way around. I'm going to get it straight. Hang on a second. So they found that the measured torque is actually bigger than the calculated torque. So if there were fewer coils in the loop, answer A, that doesn't make sense, because then that means that the measured value should end up being lower than the calculated, because they use the number of coils in the calculation. Same thing for B. Here, if the current is actually higher, if they measured a current that is actually higher than the actual value, then again, the measured value should be lower than the calculated value. It doesn't match up. So C is the only one that works. The measurement of the magnetic field is smaller than the actual magnetic field. If the actual magnetic field is bigger, that will increase the torque, because in the torque NAIB, B is in there, is directly proportional. So that means more torque. That was that problem. All right, moving along. Okie dokie. Here we go. 8. Oh, everybody's now. I know everybody's favorite. I think this. I think you should have done well on this, but then again, we've got two wires that pointing opposite directions. Opposite wires repel each other, and they exert forces on each other that are equal to the force that the other one exerts on the first. Okay, Newton's third law. So those two things put together gives you the answer of D. All right, let's keep looking here. Okay, so here we go. We have a wire with an Amperian loop in there, and we're asking for the field at that point, how it depends on the current. And I'm kind of reading this backwards. I'm having a little bit of trouble. I wish I could switch my screen. I'm just not good at this yet. Maybe I can get better at this. That would be good. Okay, so the question is, two things. Will the magnetic field depend on the total current? Is it directly proportional? Well, yeah, that makes sense. It has to. That's just dumb. I mean, hello. Okay, it's directly proportional. And the thing is, the ratio of the current through the center loop compared to the whole is the ratio of little r squared divided by big R squared times the total current. And those two things put together gives you B. And I think we talked about that actually in class. I don't know, can't remember if there were people missing that day. I think that was one of the last days when we were running out of people. Okay, so we also looked in class at this one actually, and it's also taped, I believe. Taped, how old am I? Okay, so here's a magnet, and we have a wire going through that. And there's a force on that wire due to the magnetic field, because magnetic fields exert forces on currents. And the force on the wire is down. That in turn means that the force on the magnet is up. That's Newton's third law. And therefore, it must be true that the normal force that's measured by the scale would be smaller. Moving along. Halfway through. Okay, good. You can't yell at me, but you can comment if you want to. Everybody knows how that works. Let me see if there are any messages over here on the physics. C group, no. Okay, good. Let's take a look over here. So this was, I hope, pretty much, yes, Sam. Magnetic field always goes from north to south. Well, no, not inside the magnet. Well, let's not think about that. So I'm just going to say yes. Okay. Here we go. This one should have been a gimme almost. It's a magnetic field and you have a charge entering it. It's a negative charge. Is it? Electrons. Yep. And they are deflected upwards. Now, the whole thing is point your fingers opposite the direction of the motion of the electrons. Curl your fingers in the direction of the magnetic field, and your thumb indicates the direction of the force. The only trick here is that this time they're not giving us the direction of the force, the field, they're giving us the direction of the force. So you got to kind of be like, oh, okay, that's the wrong direction because this way would be better, but ow, and then here we go. So this is the direction of the current. Force points up. Whoopsie, this is not on screen. There we go. And then you curl your fingers in the direction of the magnetic field so it's out of the piece of paper, as you can see. All right, so here also kind of a gimme. We've got a loop. We have a current in there, or an electron circling, I think, and it's saying, okay, no work. Why does it do no work? I love the second answer, that moving charges don't have charge or something. What does it say? The electron is moving, so it does not have a charge. Ha, ha, ha. Okay, anyway, so part C is correct. To do work, a force must not act at the perpendicular angle to the motion because, and this is kind of what I always come back to, a force from behind makes something faster, something from the front pushes against the motion and slows it down. And on the other hand, if you're pushing sideways, you're just turning it. You're not actually making it faster or slower, so you do not do work. You can also look at it from the perspective of power. Power is F dot V, so dW dt is F dot V. The vectors dotted together, and it's magnitude F, magnitude V times sine 90 degrees, and 90 degrees sine is 0. Cosine 90 degrees is 0. Sorry, got mixed up. So FV cosine theta, and therefore no work done. All right, let's keep going here. Okay, so then we have, oh, this is just a plug and chug. So enjoy your points, I hope. Okay, so F equals ILB, and we had to find B, and that should have been pretty straightforward. All right, so here we go. So they're just asking this one, well, how would an electron move if it got into a magnetic field as shown? And they give us 5 options. And there's 2 ways to screw this. Well, there's always more than 2 ways to screw something up. But the 2 main problems that you might run into is, one is that you just basically draw the direction of the force, and I could say it's downwards kind of, and not the motion, but it needs to curve. And I don't think this looks really circular, but we're going to pretend. So it's a circular path, and it goes down. Those are the 2 things that distinguish the motion. So then D has to be the correct answer because it's downwards and curved. And again, right-hand rule, point your fingers in the direction of the current, which is opposite the direction of the motion of the electron. In this case, curl your fingers in the direction of the magnetic field, and your thumb indicates the direction of the force on your right hand. That's why it's called the right-hand rule. All right. This looks upside down. It isn't. Okay, here we go. Okay, so here we go. I'm going to push it out a little bit further. I can't even read that remotely, and I don't remember what it was about. Hang on. Positively charged. Oh, this one's screwed up. I hope you agree that the answer is wrong. I try to get this right, but I think they're wrong. So I'm not going to count this, and I'll go through, make sure your scores are adjusted appropriately. It's a little hateful problem here because the problem itself is relatively straightforward. And then they got the ruler and want to screw you up with the ruler because they don't have it at like 0 and 0 or whatever. So this should remind you of two charges creating electric field equal to 0 at some point, kind of like that. All right, so this is a similar problem. We have the magnetic field being produced being inversely proportional to the radius. Okay, so not radius squared. And because the currents are in a ratio of 3 to 1, the distances should be 3 to 1, with the spot that's closest to the smaller current being the one where we have the magnetic field equal to 0. Now here's an interesting question. Is that the only place, or could we come up with another place? And I think we could. On the other side of the current, there's another spot. And how far away is that? 0.2 over, I think, from the small current works as well. And they don't have that as an option, I hope. So that would have been 0.9 meters. Oh, shit. They do. What? Oh, the directions are wrong. Hang on a minute. 0.9 meters does not work because they're in the same direction at 0.9 meters. Hey, I made a mistake. So the magnitudes of magnetic fields at 0.9 meters are also the same, but they're both towards us, and therefore they would add together. At 0.6 meters, they cancel. Okay, so I was trying to be all smart about it, and I wasn't. Oh. Why was it not 0? Hannah, you mean the... Wait, what? Which one are you referring to now? That was the weird north one. Okay, this is the one I think that Justine asked me to hold closer. Maybe, I'm not sure. Like this one. Okay, and I think it didn't work out. I get that the magnetic field is eastward. All right, I'm not sure. And then maybe this one. That's 17. Okay. Is this the other one? Okay. No, 0 is not an allowable answer. And 0 wouldn't work because it's 0. That doesn't make any sense. Did you mean 0.1? Okay, so in order for this to work, the distances have to be in a ratio of 3 to 1. Okay, so you need to be closer to the current I than to the current 3I, and it needs to be in a factor of 3 to 1. If the circle spot that you see in between that's closest to is 0.1 away from the current I is 0.1 meters away from I and 0.3 meters away from the 3I. Therefore, the magnetic field strengths will be equal to each other at that point, and the directions are going to be opposite each other, which we need in order for them to cancel each other out. So that's why that position works, which is at the position 0.4 meters. Sorry, 0.6 meters. Couldn't see, sorry, 0.6 meters. Sophie! Door! All right. Okay, here's another one that was screwed up. And I thought about it quite a while, and even with what I think they meant to make the answer, something didn't work on the PDF production or something, and eliminated smaller, equal, greater than signs. I just still think this is not correct. Either way, I'm not counting this question. the two cylindrical shells will create magnetic field, of course, according to, if you do an Amperian loop, you can figure that out. So for example, in the center of this area, there's certainly no magnetic field because you make a little dotted line there and there's no current going through there. However, that doesn't make any sense. I shouldn't be able to, oh crap, there's another spot actually. Sorry, I just realized that. So there would be one more spot inside the outer shell where there's also zero magnetic field, because at that point we would have the total current inside it be zero, because the outer shell has more current than the inner shell. Therefore, it would, any place further out, certainly have zero magnetic field, but you'd have to find a spot inside the outer shell, and that point there's also magnetic field equal to zero. But the answers were screwed up either way, and therefore I'm not counting this question. Hope that makes sense. Okay, here we go. We have magnetic, a little bit schnickly here. We have two wires that create magnetic field, and it looks like, oh, they're all going to be different, but actually at that point specifically, they both create magnetic field in the same direction. So they add at that point straight up. So you have 1 plus 1 at that time. Now you double one of them, that goes from 1 to 2. So effectively you now have 3. So your magnetic field went from 2 to 3. So it increased by 50% or went to 3/2. So I think Eric is asking back to this one. I believe the correct answer would be somewhere between, so anywhere between 0 and R, and there's a spot between 3R and 4R that is also have zero magnetic field, unless I'm wrong, which is possible. But 3R itself, how was the question asked? So in which of the following regions can the net magnetic field be zero at some non-zero finite distance? So everywhere for little r smaller than big R, and then there is one radius between 3R and 4R at which the total current inside is zero, and therefore at that point the magnetic field